Okay, so let's get started. So today I'm just going to cover graphical models, which Professor Mitchell just started covering on Wednesday. But we didn't really get through that much because we were covering finishing off the previous material at the beginning of the class. So I just want to make sure that you guys have enough to do the assignment that's due next Wednesday. So let's see. So the first thing I want to cover is just go through, review some of the concepts that will be very useful and kind of necessary because you kind of need to know like have a good foundation of probability theory to really understand graphical models. So I'm trying to go over some of those concepts. So the first thing is, suppose I just have two die, six-sided die, and I roll them. Can you guys see that? Okay. A little bigger? And I want to, suppose I know the probability, the joint probability, the probability of combinations of both dies. So I know the probability that die 1 is 1 and die 2 is 3, right? I know the probability that die 1 is 6 and die 2 is 1. I know all of them. I can draw this out in a grid like this. So these are just my event space, my probability space, right? This particular event is when die 1 gives me 3 and die 2 gives me 2, right? This one is die 1 is 6 and die 2 is 6, right? And basically I just want to illustrate the following fact. If I want to compute the probability of just one of the die being a certain value, say, and I can sum over the joint. Yeah. So this is the probability of die 1, say, being equal to 4 is this space, right? Or this is 5, my bad. But you can see that it's a sum of the individual probabilities over the possibilities of die 2, right? So that's basically just illustrating this point. And this is pretty useful because it's a pretty fundamental fact from probability theory, and we're going to use it to do inference in graphical models. Okay. So before I get to the definition of a graphical model, I want to just go over the definition of of a probabilistic model, a more basic concept, which we've seen a couple of times, but just to make sure we have the definition. So a probabilistic model is just a collection of random variables that are somehow related to each other, and you typically describe how one is related to how any one random variable is related to the other random variables. Like this is, for example, a probabilistic model. I have two random variables, the first die and the second die. So and you can kind of think of it intuitively, or one way to think of it intuitively is as an extension of deterministic models. Like if I have equation and I ask like what is the value of y when x is 0, you can tell me that. And these equations, like in general, deterministic models, systems of equations, are very useful for describing things about the world, modeling physical phenomena, a lot of other phenomena, and we can use them, to tell us a lot about things that that may not be necessarily immediately known to us. Probabilistic model is basically an extension of this, where you can think of the variables as being random. So instead, if I ask if x is drawn from a normal of mean 0 and standard deviation variance 1, then what is the value of y? And that's useful, especially when the phenomenon you're trying to describe has uncertainty or randomness. And there's a lot of uncertainty in real-world phenomena that we'd like to model and capture when we're doing machine learning. Okay. So, move this up. I can't move this up. Let's go here. Let's go here. So, we use a lot of words like joint, prior, likelihood, posterior, and I just want to make sure we pin down the definition of those words to make sure that you guys understand what we're talking about when we say those things. So the joint distribution, suppose I have a probabilistic model with the following random variables. I have x1 through xn, and I have theta 1 through theta m, let's say, right? So I just have n plus m random variables, and they're somehow related to each other. I'm not going to tell you how or why, because this is a general definition. The joint is given by so this is the joint probability, right? So the joint distribution is the distribution over all of the random variables in your model. And the joint probability is the probability of all the random variables in your model taking on specific values. As a shorthand, sometimes people will collect random variables together that are similar, and they'll just write, right, this x just means all the x's, the theta just means all the thetas. Okay. And so suppose now that I've observed some of my random variables, right? Suppose I observe all the x's. And in machine learning, that tends to be your data, the data points that you observe. Then I can define 3 other distributions or probabilities that are commonly used. So this is my prior. So the probability of only the things that are unknown is the prior. Sometimes you also just say what is the prior on a particular random variable, like theta I or theta 2, right? And that's also the probability of theta 2 is the prior on theta 2. The likelihood is the probability of your data, your observed random variables, given the unobserved random variables, the unobserved parameters, the hidden information. And this quantity is what you try to maximize over your hidden information when you're doing maximum likelihood estimation, MLE. And the posterior is just the probability distribution of your unknown random variables given your observed random variables, x1 through xn. Any questions on those definitions so far, including? Nope? Okay. Okay, so let's just give you a concrete example. So here I have 5 random variables, and I'm telling you how they're dependent on each other, right? A and B, they're just drawn from Bernoulli's with probability 1/2. So you're flipping a coin. With probability 1/2, it'll be 1, and probability 1/2, it'll be 0, right? C is just a sum of A and B, right? So if A is 1 and B is 1, then C will be 2. And same thing for D and E. So suppose I observe C and E. So here's a question for you guys. What is the joint probability in this model? The probability over which random variables? Say again? I can't hear you. Could you say it one more time?
I said ABD.
ABD? All of them. Yeah, exactly, all of them. That's right. So the joint probability is a probability over A, B, C, D, and E, right? And what's the prior? Yeah, so yeah, A and B and D is your prior probability, right? What's my likelihood? Someone else? Anyone?
CNE over ABD.
Yep. And the posterior is just probability of A, B, and D given C and E. Does that make sense? Okay. Okay, so this is nice, but there's a pretty convenient way to represent this graphically. And I'm just going to draw it here. So this is a Bayesian network. It's a particular kind of graphical model. And here, this network, this graphical representation corresponds to this probabilistic model. And when we say graphical model, we usually mean both the graphical representation and the probabilistic model together. They constitute the graphical model. Any questions on that so far? So you can see kind of how they correspond. C is randomly generated using A and B. It's not really random, but you can kind of think of it as having probability 1 of being equal to A and B, A plus B, right? D is randomly generated on its own. It has no parents, right? So it doesn't depend on A, B, C, or E, right? E depends on both C and D. So it only has C and D as parents. Okay. And what's really nice about this model is that it tells us a way to simplify the joint distribution, the probability of A, B, C, D, and E. And I'll show you how exactly. So the Bayes network tells us exactly how the joint probability factorizes. And it's just equal to the product over all of the individual probabilities of the variables given its parents. So the first one is A. A has no parents, so it's given nothing. B has no parents either, so it's given nothing. C has A and B as parents, so this term is probability of C given A and B. So this is the factorized form of the joint distribution, and it's really useful because instead of having this, this massive joint, we've simplified it into smaller probabilities. Okay. So for example, A, B, C, D, and E were all binary. In this case, they're not, but if they were, for example, how many possible values does this probability have, the joint probability? Right? If I were to make a table of all of the possible values of A, B, C, D, and E and the corresponding probability, how many rows would that table have? Suppose they were all binary. They can only take 2 values each.
Unique values, right?
Sorry?
Would it be less because it's unique values?
Oh, not necessarily unique.
Okay.
So just counting all of the possible settings of A, B, C, D, and E. Right, and 32. So it's 32 because it's 2 to the 5, right? Yeah. Because there are 5 possible values, each one can take 2 possible, there are 5 variables, each one can take 2 possible values, so it's 2 to the 5 possible values for all of them. But on this side, this is a little simpler because A can only take 2 values, so this probability only has 2 values. This only has 2 values as well. This one also only has 2 values, but it depends on the values of A and B. So this is gonna be a function of A and B. So
P of C given A, B have 2 values, so it could be 0, 1, or 2, because it's A plus B.
yeah. I mean, for a given setting of A and B, C can only take 2 values, but there are 2 squared possible settings of A and B, right? So you're right in that if you're also varying A and B, you get 2 to the 3 possible values in that table. Same thing for E given C and D, right? So this is very useful, and this we can get immediately from the graphical model how the joint factorizes over all of the marginals, the simpler probability distributions. Yep?
So how many rows exactly does the second factored expression? Like how would you construct one probability table?
So, I mean, you wouldn't construct a single probability table. You would basically just want a way to efficiently compute the probability for a given setting of the variables A through E, right? And this factorization tells us how to do that easily with the largest table size being 8, right? I basically have to look up for each table what the corresponding probability is and multiply them together, as opposed to having look up in a table of 2 to the 5 rows. So that's the advantage that this gives us. Okay. Any other questions? Okay. What time is it? 25. Okay. So another thing I want to mention is that when you have variables that are observed, that's typically represented in the graphical model as shaded nodes. So if C and E are observed here, then I'll just shade them. That's just a common convention. Okay. Another really useful thing about a graphical model is being able to tell which variables are independent of other variables. And you can answer that question even if you're conditioning on other variables. That's called conditional independence. So Tom covered a couple of rules in class on Wednesday, but he said that those are sufficient conditions. They won't following those rules won't give you all of the possible conditional dependencies. There's a nice technique or algorithm for getting all of the necessary independencies from any from any graphical model. And I'm going to introduce that right now. It's called lots of things. D-separation is one name. Bayes ball is another cool analogy of that algorithm. I'll cover it right now. So I'll shoot here. So just I want to be able to answer things. So here's a question for you guys. Is the variable A independent of B? Yes. Why?
It's just picking values from 0 to 1.
Yeah, I'm drawing them independently of each other. I'm not using any information from the other variable when I generate them, right? Now, what about if I'm given C? Is A independent of B conditioned on C, given that we've observed C? So one way you can show this, and it's kind of difficult, is to use this to then show that the probability is factorized, that the probability of A and B given C is equal to A given C times B given C. That's the definition of conditional independence, right? But that's kind of hard. So instead, I'm going to give you a set of rules which you can use that'll give you all of the conditional dependencies for that graph, or for any graph. So the reason why it's called Bayes ball is imagine a ball bouncing from one variable to another. And it's traveling through the graph, and it wants to get to the other variable. If there's a path that the ball can take where it reaches the other variable, then the two variables are dependent on each other. Okay? If there is no such path, then they're independent. And there are a couple of rules for when the ball can pass through nodes in the graph. And here are the rules. So if you have an unobserved node, the ball passes through it easily. If the arrows are pointing in the same direction, going in and then going out. Okay? Same thing as if the arrows are both pointing out and it's unobserved. But if they're both pointing in, sometimes it's called a collider node, then the ball cannot pass through. Okay. But if they're observed, then the rules are reversed. Okay, so these are my rules for the Bayes-Bell algorithm. So now I'm going to ask the question again. This is not a good eraser. Okay, so only C is observed now, right? So is A conditionally independent of B given C? It's dependent, right? And it's because it can pass through the observed node because the arrows are both going in. Okay? So here's another case. Suppose I observe E now. Yes? A is dependent on B? Yeah. Is that a question? I'm sorry. Yeah, that's right. So if A is independent of B given C, right? But if I'm given nothing at all, then the ball can't pass through C because it's unobserved, right? It'll be unshaded, and so it'll bounce back. And so A and B will be independent, which makes sense because that's the answer we gave earlier. Because given nothing at all, I know that A and B are drawn independently from a Bernoulli distribution. Yep.
Sorry, I got confused. So if C is an observed variable, then A is dependent on B.
Yes.
C, right?
Yes, that's right. Yeah. So given C, C is now shaded, and now the ball will pass through the shaded node. This rule. And A and B will be dependent. Does that make sense? Yes?
How's the first case possible? The first case, an arrow should unobserved node and off of unobserved.
This one? Well, suppose, I don't know. This X is just a random variable that's normally distributed, right? With mean 0, variance 1, so it's just some real number. Y is equal to X plus 1, let's say. And Z is equal to Y plus 2. Right? Is X dependent, is X conditionally independent of Z? No, not necessarily, because if you haven't observed X, then you haven't observed Y either, right? So the shading only tells you which variables you've observed. So I can define this differently as well. Say Y is a normal with mean X and variance 1. And I can make Z the same thing. Right? Then Z clearly depends on X. The two are definitely not independent of each other, right? So that means that the ball has to pass through Y. Does that make sense? Okay, cool. Any other questions?
So in this case, Z is dependent. They're all dependent.
Yeah, everything is dependent.
Even X.
Well, I mean, you have to say that one variable is dependent on other variables, right?
Yeah, okay.
So,
Y is dependent on on X, Z is dependent on Y, and then therefore.
Exactly.
So we're saying that X is dependent on Y? No, right?
Well, no, they're not independent.
X is independent of Y, right?
X is not independent of Y.
X can choose any value we want, but Y will be dependent on X. Right?
So by dependence, in independence, so X and Y will be independent if right?
Suppose like X is a random variable of coin toss, and Y is like if I get 1 head, I will take Y will take a value of 2. If it's a tail, it will take a value of 4. So X is independent of Y. The coin flip is
No, independence isn't like, it has nothing to do with like causation or anything. It doesn't tell you the order in which you generated your values. Independence tells you something about whether you can gain information about a variable given another variable, right? So like if I see that Y is like 100, right, then the probability of X will change. I mean, I'll know that X will probably be closer to 100, right?
yes. So X is in general X is independent of Y, but if we have Y as observed variable, then it is dependent, right? X is in general an independent
So
distribution from Y.
okay, so let's,
If we have Y as an observed variable, then we can say that X is dependent on Y observed.
well, let's, the definition of independence is this. This is the most fundamental thing. If you can show that this is true, then that means X and Y are independent. And in this case, that's not true. And I can take the question after class and answer it in more detail if you want more details. Okay. Yep.
So I just want to check whether I understand this correctly.
Sure.
So it's X given Y and Z given Y independent. X given Y and Z.
So you're saying just shade this.
So then X and Z should be independent, right?
They're right. That's right. They're independent. Yeah, because you have this case. Any other questions? If you're interested in why, when Y is unobserved, X and Y are still dependent on each other, then I can answer that in more detail after the recitation. Okay? Because that requires a bit more math. Okay. So let's just go through a few more examples. Where's the eraser? So what if I made this unobserved? And I kept E observed. So given only E, is A independent of B? Anyone have a guess?
Independent.
But here's one possible path that the ball can pass through. It can go from A to C and to E, right? Because it's going through the top left rule over there. And then back through E into C up to B. So they're actually dependent.
That's because we not C. Because we're observing E, right?
We're only observing E. C is not observed, yeah. So the ball can pass through C into its ascendance and then back up through C into B. Make sense? Okay.
So your phrase was, is B independent of A or vice versa?
Is A independent of B given E? Yeah.
The answer is no, or yes, it is.
They're dependent, yes. Yeah. Okay, how about one more? D and A given E, just E. Are they dependent or independent? D and A given E. Independent? Why? Dependent, yeah. And why? What's the path?
From A to C to E to D.
Yeah, exactly. A, C, E, D.
So it can go up a different branch tree.
Yeah. Okay. So yeah, so this algorithm will give you all of the necessary conditional independences in a graph. Given any variable that you want, you can tell whether any two variables are dependent or independent. Okay. So I want to use this, let's use this one. Okay, so this, oh, the backboard. Good? Okay. So now, how much time do I have left? Okay, not too much. So now I want to say, how can I do inference in a graphical model? So inference is basically trying to obtain information in some way about your unknown parameters or some unknown variables, given information like that I observe some other variable, right? So here's a question. In that model, what is the probability that A is 0, given that E is 0? Anyone have a guess? I'm using this model, by the way.
It should be possible only when B and D both are 0.
Yeah. So if E is 0, that means that C plus D is 0, but each of C and D can only take either a non-negative probability. They can't be negative, right? Sorry, they can only take a non-negative value. So that means that both C and D have to be 0, and that also means that A and B also both have to be 0. And so what's the probability that A equals 0 given E equals 0? Well, it'll be 1, right? Because it's the only possibility. Okay, so here's another one. Yeah.
0.
Why?
It can never be possible. Oh, I'm sorry. It can be possible.
Yeah. This is a bit trickier.
So either B has to be 0 or D has to be 0. And the other one should be 1.
Yeah. Yeah, so you can probably reason about this in that model and obtain a probability. But what if that model were a lot bigger, a lot more complex? And I need some sort of standard way to compute this kind of probability without having to rely on the model being small enough for me to reason through, right? Because in machine learning, you're going to deal with lots of data sets where you have millions of variables, random variables. So I'm going to do the following, and this is one way to do inference. And hopefully you'll see that you can apply this method, this technique, to doing inference for lots of different kinds of models. So using Bayes' rule, I can write this out as the joint divided by the probability of the condition, right? And if you remember, actually it's underneath this board, this rule, that the probability of anything is the sum over the probability of the joints. I can introduce variables like D2 here, but I have to make sure I sum over them, okay? So here I'm adding variables B, C, and D into the probability and summing over them. Any questions about that step? And then what can we do next? So yeah.
Why is it B and not C? Can you just explain why it's
Oh. Thank you. So any guess on what the next step is? Yes, I can factorize, this is the joint distribution. And that's the reason why I wanted to get this, because the reason why I wanted to add all the variables into it, so then I can use that. So I'm not going to rewrite this. I'm just going to. Good? So, any ideas on how I can work with this? Simplify it.
You can put PA into PB into sigma B. Separate factors.
Yes. Good. So I just move the B sum all the way to the right-hand side. Yep.
Given P of C, given AB is still. Because it also.
Oh, you're right. Yeah, yeah. Did I do that? Okay. Okay. Does everyone see why I had to do that? It's because there was still a B inside the C term. So there is no way I could have just brought it outside, right? Okay. Okay, so let's just compute this. So this is just equal to, let's see. So what are the possible values of B? Right, I'm just writing out the sum here, and I'm substituting in the possible values of B, because this is sum over the values of B. And B equals 0, B equals 1. And what's the probability of B equals 0 and B equals 1? Yep, 1/2. So these I can't really compute yet because I have the sum over C here, but this is good enough for now. Yeah, actually, let's. So let's compute this for the possible values of C. Okay. So if C is equal to 0, and let's say we're interested in when A equals 0. Then this will be the probability that C is equal to 0, given that A equals 0 and B equals 0. What's that probability?
That's 1.
1. Yeah, because C is A plus B, and if A and B are both 0, then C is 0. That's 1. Probability that C is equal to 0 when A is equal to 0 and B equals 1? 0. This is 1/2. And what are the other values that C can take? C can take either 0 or 1, or 2, right? Because it can be a sum of both ones. So let me move this up. So when C is equal to 1, what's the probability that C is equal to 1, given that A is equal to 0 and B is equal to 0? C is equal to 1, given that A is equal to 0 and B equal to 1? 1. And C equal to 2, given that A is equal to 0 and B equal to 0? And C is equal to 2, given that A equals 0 and B equals 1? 0. Okay. So notice that this term I've kind of simplified. Now it only depends on C. Right? If C is equal to 0, this entire sum will be equal to 1/2. If C is equal to 1, it'll be equal to 1/2. If C is equal to 2, then it'll be equal to 0. Okay. So let's just do the next step, which is, I mean, there are a lot of options here. You can compute these in different ways, but the trick is, I mean, you can kind of see what I'm getting at. Like, you want to push these sums as far into to the right as possible. And that'll make the computation there a lot simpler. So let's just sum over C next. Let me put this up. And I'm just going to call this f of C, just to be succinct. Yep.
The PA can be taken outside the whole thing, right? Because it is independent of everybody.
You're right, that's good. Does everyone see that? Does everyone see why P of A can be taken out entirely? It's independent of everything, right? But the problem is that, actually, yeah, that's right. So I can do the following. Right, that's fine. And this thing I just replaced with f of c, because that's what we computed earlier. So let's just compute this term, this now. So this depends on a couple things. Depends on d, and we know e is 1, so we can just go with that. Okay. So when d is equal to 0, so let me write this out. This is just let me erase this. So I'm just writing out this sum over all the possible values of c. C can take 3 possible values, right? It can be 0, 1, or 2, because it's a sum of a and b, right? A and b can each be either 0 or 1. And so this is just, I'm just writing out this, substituting the values of c for each term. It's a little small, but it's kind of a long expression, so kind of hard to work with. But let's just evaluate this. So these depend on d. And how many values can d take? What are the values that d can take? 0 and 1. So let's just do d equals 0. So what's the probability that e is equal to 1, given that c is 0 and d is 0? 0. Probability that e is equal to 1, given that c is 1 and d is 0? That's 1. And that's multiplied by f of c equal to 1. And f of c equal to 1, we computed there, is 1/2. Okay? And the other d value is d is equal to 1. What's the probability that e is equal to 1 given that c is equal to 0 and d equal to 1? 1, because e is equal to c plus d, right? Times f of c equal to 0, which again is 1/2. Plus the probability that e is equal to 1 given that c is equal to 1 and d is equal to 1. 0, because e is equal to c plus d, and that means e would have to be to 2, right? Okay, so now I've computed this thing. Okay, we're almost done. So now I have that the original expression, p of a equal to 0 given e equal to 1, equal to p of a over p of e times the sum over d I'll just call this f of d, or g of d, just to be right. And now we can compute this term. This is the last sum we have to compute. So this is p of. So what are the possible values that d can take? 0 and 1. Right? And the probability d equal to 0 and d equal to 1 are? Anyone? Yeah. And g of d equal to 0, we found is 1/2 there. And same thing for d equal to 1. So all of this in the end turned out, this sum turned out to be 1/2. Okay. So now, what is the probability of A equal to 0? 1/2, right. And the probability of E is more difficult, right? 3/8. How do you get that? Yeah, that's basically. So in this case, you can kind of just see how many possible settings of A, B, and D give me E equal to 1 when the sum of all three of them is 1 and 3/8. But in general, it's more difficult to compute. So there's another way you can compute P of E without explicitly, listing out the entire table. And that's just to drop it, basically. I know that P of A equal to 0 given E equal to 1. The only thing that's varying in this probability is A. This distribution is over A, right? A can either be 0 or 1. But I also know that probability distributions must sum to 1. They always sum to 1. So what I could do is just compute right? And this is just some normalizing constant. Let's just call this 1/k. And by using this sum, I can compute k. So I can basically just drop this and just say that probability of A equal to 0 and given E equal to 1 is proportional to 1/4. It's just some constant times 1/4. That constant I don't know, but I can figure it out at the end because I know that the resulting probability distribution must sum to 1.
Where would the 1/4 come from?
Oh, this 1/4 came from probably A times 1/2. Probably A equals 0 is 1/2. So 1/2 times 1.
Because you took out E.
Oh yeah, exactly. So I just took out the E. And it's no longer equals, it's just proportional to.
It's 1/2. Okay.
Yeah. So that means that in order to compute the normalizing constant, I have to compute this thing when A is equal to 1. All of this thing when A equal to 1. And it helps to have done work such that it's not hard to just go back and look at the probabilities and modify them where necessary. Because you don't want to go through all of this again. There's a reason why we do this on computers as opposed to by hand. But this is very good for understanding how, in principle, how a computer would be able to do inference in a graphical model. Okay, I think I'm out of time. Way past time. Yeah. So, any questions on what I've done so far? You can say this from the very beginning too. Basically, at the very beginning, at any step in my derivation, for any terms that don't depend on A, I can just say that I can just drop those and say that the expression is proportional to the result. I can just drop the terms that don't depend on A. And then at the very end, I kind of reconsider them by making sure that everything normalizes to sums to 1. And I basically get that back for free by computing the normalization constant. Because that's the only role that those terms play is in the normalization constant. Okay.
So this works better probably when, because in this case it's just Bernoulli for A, B, and D, right? So like we could have just taken 0.5 and done the multiplication, right? Versus doing like the summation of all possible values and come up with the same thing, no? But when you have like, a giant, variant distribution, it seems like this would be a better approach. Does that make sense?
So I'm not sure what the first approach you mentioned was. Could you repeat that? If you prefer, you can ask me after the presentation. That's fine. Okay, let's do that. Any other questions before we end? Okay, cool. So if you have any questions, feel free to come down. I'll answer them. I can answer your question about that thing. So, cool. Thanks.